Hello, welcome to this lecture on boundary layer theory. And in this lecture, I'll be discussing Prandtl boundary layer equations. Prandtl boundary layer assumptions and equations. So, okay, this is basically it is for 2D boundary layers, two-dimensional boundary layers. And the two-dimensional flow is governed by the viscous flow is governed by the Navier-Stokes equations consisting of the continuity equation, the x momentum equation, and y momentum equation. So basically, these are the equations. So the Prandtl has made certain assumptions for the boundary layer flow, such that these equations are simplified, so that it can be solved much more easily compared to solving the Navier-Stokes equation, at least for the boundary layers. So I will draw the schematic of a boundary layer over a flat plate. No, this is a bound layer. Okay, in a flat plate, it could be any other body in which the body surface coordinate is represented by x, and the body normal is drawn along the y axis. Axis. So the bound layer is drawn is like this bound layer. This is actually the bound layer thickness, or the bound layer. Bound layer itself is shown like this. So it actually indicates the points on this curve indicates the edge of the bound layer. The velocity distribution at any point um, any point could be so. This is the velocity at the edge of the bound layer, and this is going to be the potential flow velocity, and this is the solid surface, and there is a free stream, flow, free stream flow, approaching the solid body at certain velocity, infinity, uniform flow. And this kind of a bound layer is sets up, and this distance is delta, and delta is a function of x. So all that are the features of bound layer. So the bound layer thickness. Okay. So the mean flow is or mean flow at the inlet is of this kind of uniform along the x direction, and the potential flow velocity also u is also along the x direction, and the boundary is a region where there is a velocity variation from 0 to the potential flow velocity or outer layer velocity. This is U is potential flow velocity. Tangent to the body surface. Come on under. Okay, that is potential velocity is always tangential to the body surface. There is no normal command velocity over the body surface. Hmm. And the boundary layer is a region where there's a velocity gradient, and there is a displacement. That way, there is a component of velocity small u and small v, and small u is a function of x y. Small v is a function of x and y. This is a vertical component of velocity. This is a not no, component of velocity transfers to the direction of flow along the body surface, and this is the u is the velocity component along the direction of the body surface, parallel to the body surface. That is small u and small v. So the Prandtl boundary assumptions are 1, and the v is much smaller than u. The vertical component of velocity is much smaller than u. So here the boundary layer is shown as an exaggerated size, but actually the delta is much smaller than this. So for any value of x, the delta is much smaller than x. But this is just for the purpose of showing it has shown at certain height for the sketch in the sketch. But actually it is like this. And small u varies from 0 to capital U, right? So it is on the wall, it is 0, but in general you can be approximated to have an order of magnitude similar to that of capital U. So this is written as u is having the same order or the similar order that is that of capital. And another important assumption is the gradients along the x direction reduces with as x increases. So that way dou by dou x is of the order of 1 by x. For larger distances, the gradient along the x direction reduces. The fifth one is dou by dou y is of the order of 1 by delta, because the velocity gradients exist in the vertical direction exists over a distance of delta, and beyond delta for y greater than delta, dou by dou y is 0. So as y increases, the gradient reduces. The gradients are more here for smaller values. So as the y increases, the gradient reduces, and it scales as dou y as 1 by delta. So these are the basic assumptions Prandtl has taken to simplify the Navier-Stokes equation for the boundary layer. So now we'll see the first equation and do an order of magnitude analysis to see how does v is. So we'll take continuity equation first. Let's take the continuity equation and see and perform an order of magnitude analysis based on the assumptions about the boundary layer, which just now I have explained. So okay, that order of magnitude analysis. So we know we have explained that dou by dou x is of the order of 1 by x, and u is of the order of. So this first term is of the order of u by x. That is, there are two terms. The first term is of the order of u by x. So and the first term and second term is equal to 0. So the second term also, that is dou v by dou y also should be of the same order, but the negative sign. But for order of magnitude analysis, we will not put the sign. So dou v by dou y also is of the order of u by x, and dou by dou y, the approximation is it's one is of the order of 1 by delta. So the continuity equation suggests one thing, that v is of the order of u delta by x. These are the order of u delta by x, and this term is u by x of the order u by x, which is somewhat having this u is high and x is also high. Okay, it is having a nearly, you can say that it is having an order. It's an order of a ratio of a higher value term to a higher value term itself. That is of the order of 1 or something like that. Something like order of 1, this cannot be neglected. So this is of the order of 1, this is also of the order of 1. So both the terms cannot be neglected. So the continuity equation remains as such for the boundary layer, exactly like that in the Navier-Stokes equation. Now let us take that u momentum equation and see how the different terms are the order of magnitude of different terms. The order of magnitude of different terms of the u momentum equation. Let us see. So this is the u momentum equation. So we'll do the same and order of magnitude analysis. So you know, u is the order of capital U. Dou by dou x is the order of 1 by x, and u is the order. So the first term is of the order of u squared by x. The second term is v is of the order of u delta by x. That is from the previous analysis. So dou by dou y is of the order of 1 by delta. That is dou by dou y is of the order of 1 by delta, and this u is of the order of capital U. Delta cancels. So this is u squared by x. U squared by x. This is also u squared by x. Both the terms will be equally contributing, or nothing we cannot say one is higher, much higher than the other or not. Both are nearly of the equal, of nearly equal order of magnitude. So u squared by x. This is also u squared by x, and you know in the numerator there's square of an high value term, that is u squared, larger value term, and x is one larger value term. Still you can say that the whole term is having a larger value contribution. So like that. So coming to this, okay, now okay, that way these two terms are having nearly the same order of magnitude, and let us come to this term and see. See in this term, dou squared u by dou. So dou squared by dou x squared. Dou by dou x is of the order of 1 by x. So dou squared by dou x squared is of the order of 1 by x squared. So this is order of 1 by x squared, and u is the order of small u is the order of the potential velocity capital. Similarly, okay, that is about the first term. Similarly, for the second term, that is dou squared by dou y squared. That is of the order of 1 by delta squared, and u is of the order of capital U. So you see, this higher quantity, higher u is having a larger value. Delta squared is a small value square in the denominator, and this is a higher value in the numerator, and a higher value square in the denominator. This is so that way this is much larger. Second term is much larger. For example, this is of the order of some 1000 or so. This could be something like 1 or even less. So so an approximation of neglecting 1 when the other term contribution is 1000 is reasonable. So the Prandtl's reasonable assumption about the boundary layer is dou squared u by dou x squared is equal to 0. This in physical terms it is the axial diffusion. So axial diffusion means the diffusion in the x direction. So diffusion of momentum in the x direction is much smaller compared to diffusion along the y direction. So y direction is the direction of the velocity gradients, where there will be a diffusion of momentum, larger diffusion of u momentum in the vertical direction rather than the horizontal direction. So basically this term goes right. So So that is what it is for. That is what it is for the U momentum equation. So U momentum equation simplifies us with neglecting this term. So we can write it as we can write the U momentum equation for the bound layer as per Prandtl is Prandtl's theory is u dou u by dou x plus v dou u by dou y is equal to minus 1 by rho dou p by dou x plus mu into dou squared u by dou y squared, and of which we can again come to some conclusion about some substitution for this pressure gradient term. The pressure gradient in bound layer is due to what? That we'll see. For that, let us consider a point on the edge of the bound layer. So we know that inside the bound layer there are velocity gradient. Outside the bound layer there is no velocity gradient. The potential velocity is existing, and that too we consider it as irrotational outside. So the bound layer is concerned. Within the bound layer the flow is irrotational with gradients, whereas outside the bound layer is sorry, within the bound layer it is rotational. It is having rotation, it is having a curve, whereas outside the bound layer it is irrotational. So on the edge of the bound layer edge of the bound layer we can assume the Bernoulli's theorem holds good. So if let P be the pressure, at this particular point. So you can apply Bernoulli's theorem for this particular point. So Bernoulli's theorem is at the edge of the bound layer. Gives that is P plus half rho. Edge of the bound layer, the velocity is potential velocity at that x. This is equal to constant. Any point this is to. So differentiating this with respect, we can write dou p by dou x plus half rho 2u du by dx is equal to 0, because u is a function of x only. It varies along the length of the body surface. So this 2 cancels, 1 by rho comes here. So minus 1 by rho dou p by dou x is equal to u du by dx. So this equation can be rewritten. The pressure gradient can be rewritten in terms of the potential flow velocity gradient along the direction of flow. This can be rewritten. As u du by dx, and we know that this is of the order of u squared by x. This is of the order of u squared by x. Similar order quantities. This is of the order u d by dx is the order of 1 by x, and this also u squared by x plus nu into dou squared u by dou y squared is 1 by delta squared u. So these are all similar order quantities. We can cut them. Cut them. So like that, if you do one u also goes, so that we can write delta squared scales as nu x by u. So the bound layer thickness is of the order of square root of nu x by u. So this is something again we get from the x momentum equation. The bound layer thickness is of the order of square root of nu x by u. It doesn't mean that delta is equal to square root of nu x by u, but it stays as square root of nu x by u. We can so something like a proportional constant or something will be multiplied to get the exact value of delta. So something of that order. So it is again we get like that. Or if you want to write nu, you can write just nu. That is a property of the fluid. So that can be expressed in terms of delta squared. Nu will be okay. This is delta is a consequence of the kinematic viscosity, but we can also write nu will be of the order of u delta squared by x. This way also we can write. So something like this. So this will be useful in the next the application of the theory for the V momentum equation. This will be useful. So what about the V momentum equation? We are having u dou v by dou x plus v dou v by dou y is equal to minus 1 by rho dou p by dou y plus mu into dou squared v by dou x squared plus dou squared v by dou y squared. So this u scales as u is the order of capital U, dou by dou x is the order of 1 by x, and v is the order of capital U capital U delta by x. Okay. Okay, that way we can say that the entire term is u squared delta by x squared. So large value terms square on the numerator, square on the denominator. That maybe we assume that they cancel, and the term will be left out with a small quantity delta. So something that whole term will be something of the order same as that of the delta, which is much smaller compared to the term which we are discussing here. This term is of the order of u squared by x. So compared to u momentum equation, the first term of the v momentum equation is much smaller. So like that, if you look about this one, this v is of the order of u delta by x, dou by dou y is 1 by delta, and v is u delta by x. So one delta goes, so this is also u squared delta by x squared. So both the terms are of the nearly same order, but both are small, right? Now let us come and see. Okay, this also just like our u momentum equation, the first term is going to be much smaller than the second term. So this will be much smaller than the first. So we need to look at only the second term. So we know that nu is scales as u delta squared by x. U delta squared by x. And dou squared v by dou y squared. Dou squared v by y squared. Dou squared by dou y squared is 1 by delta squared. V is u delta by x. So this delta squared cancels. So this is also u squared delta by x squared. So all the terms, so this term are minor. This term is much smaller than that. So that way, the conclusion from the Prandtl boundary assumption or boundary theory is that the 1 by rho dou p by dou x is of the order of delta, or is of the order of a small value, compared to 1 by dou p by dou p by dou y here. So this term is dou p by dou y. Dou p by dou y is a very small order quantity like that of the boundary thickness compared to dou p by dou x. Dou p by dou x scales as du by dx, which is equal to u squared by x. So there is a larger quantity square. So that way, the Prandtl boundary assumptions for the V momentum equation results into the conclusion that the pressure gradient normal to the OD surface across the boundary layer, it is 0. So effectively, you can think like this. Suppose there is a boundary layer. Suppose there is a boundary layer. Suppose there is a boundary layer like this. This is the edge of the boundary layer. This is the y direction. If you are considering point 1, point 2, point 3, point 4, P2 minus P1 by delta y, if this is delta y is taken, that is equal to 0. That means that P1 is equal to P2. Similarly, you can say that is equal to P3, equal to P4. That is pressure gradient pressure across the boundary layer remains the same. So within the boundary layer, if we take a cross section, the pressure will will not be varying, but pressure will be varying along the x direction. Pressure is not varying along the y direction. So we can summarize the Prandtl boundary layer equations as dou u by dou x plus dou v by dou y is equal to 0. U dou u by dou x plus v v dou u by dou y is equal to okay is equal to okay both ways in terms of pressure gradient as well as in terms of potential flow velocity variation. We can write 1 by dou dou p by dou x plus mu into dou squared u by dou y squared. So this dou p by dou x becomes dp by dx because p is mainly a function of x. So dp by dx. So that we can write. And this in terms of potential law velocity is minus sign. So u into dou u by dou x plus v into dou u by dou y is equal to u du by dx plus mu into dou squared u by dou y squared. And this continuity equation dou u by dou x plus dou v by dou y forms two equations for u and v. Two equations for u and v. U and v are the unknowns. U v are the unknowns. U v are the unknowns. U and v are the unknowns. Unknowns. We can find out u and v by solving these two equations. Wherein capital U forms an input. Capital U is an input. That is the potential flow velocity will be used as an input. So we have studied methods for determining the potential flow velocity distribution or different bodies like circle, ellipse, airfoil, etc. So we do that kind of a solution for that potential flow velocity distribution, and that is inputted as that is given as an input for solving the Prandtl boundary equation. So so this has to be solved. So this is again non-linear equation, partial differential equations. Now there is some more simplification you can obtain in the case of a flat plate flow. Suppose you are having a flow or a flat plate. The advantage is that the simplicity is that you are having we are having we are having a uniform velocity free stream that is called u infinity, and in the case of a flat plate flow, so the same the potential velocity is equal to u infinity, does not change, and is a constant with respect to x. So du by dx will be equal to du infinity by dx, that is equal to 0. So in the case of a flat plate, we can have a more simplification for this situation. So this equation simplifies it to further to like this. This is equal to 0. So this is negligible. So this becomes mu into dou squared u by dou y squared. This is for the flat plate. This is for a flat plate. So the solution is somewhat easy because there is no potential flow velocity, or there is no pressure gradient. It is a flow without any pressure gradient. That is zero pressure gradient flow. This is the family has made developed this Prandtl theory and equations in the year 1904. That is something very much contributing to the development of theories in fluid mechanics. He has developed the theory in 1904, and this is actually a mathematical problem of solving two unknowns u and v with some boundary conditions. The boundary conditions are Northley boundary condition v is equal to 0, v is equal to 0 on the wall, and then maybe you have a velocity bound layer with velocity u at the edge of the bound layer. So at this distance, so do u by do y is equal to 0. At y is equal to delta, at y is equal to delta, That is another condition. So this is u is equal to u of y is equal to 0 is equal to 0, b of y is equal to 0 is equal to 0, and dou y is equal to 0 at y is equal to delta. So at y is equal to delta. So these are the boundary conditions. So these are the boundary conditions. So we'll see in next lecture how Blasius has solved this problem of solving U and V over a flat plate bound layer in the next class.